Good morning, class. We are looking at section 5.4, indefinite integrals and net change theorem. Again, we had a lot of formulas, okay, basic integration formulas that we should be comfortable with. We covered areas and distances and the idea of a left endpoints, right endpoints, midpoints, and the actual area under the curve, which is taking the limit of the Riemann sum as n goes to infinity. The definite integral, various parts of that. The FTC, okay, so we discussed the following. We looked at the definite integral of a to b f of x dx, which is f of b minus f of a, and capital F prime is lowercase f. The derivative of f of t dt as we integrate from a to x is lowercase f of x. If you take the derivative of the integral of a to g of x f of t dt, you plug in g of x and you multiply by g prime. If the top and the bottom are both functions, you plug in the top function times h prime, and then you plug in the bottom function times the g prime. They both come from the fundamental theorem of calculus and the chain rule class. Now, the indefinite integral and the net change theorem, in short, is nothing but the FTC1, if you will. The integral of a to b f of x dx is capital F of b minus f of a, okay? The integral of a rate of change in the net change, okay? So if you're given a rate of change, then the net change theorem or the accumulated change theorem gives you the answer as follows, okay? And this principle can be applied to all the rates of change in the natural and social sciences. So let's look at some examples, class. And let's put this in slideshow. So in short, this is what matters, okay? So let's recap by looking at a few integrations, class, as practice, and then we will look at applications in a moment. First, I figured just to refresh your memory about integration when things are a little bit more interesting. For example, we are looking at cosine over sine squared of theta. And when you're dealing with a trigonometric function, you should always look for a way to simplify if it is possible, okay? If not, then maybe some sort of a substitution is in order. I hope you realize you can write this as 1 over sine times cosine over sine. Why are we writing it as such? Now we have a cosecant times cotangent, and we know the derivative of cosecant is minus cosecant cotangent. So therefore, the integral of this must be minus cosecant theta plus c. A simple case where we manipulate the given integral such that it becomes an easy case of anti-differentiation for trigonometric functions. Here's another example. 10x to the power of 4 minus 2 secant squared, and we want to integrate that. Well, let's do piece by piece. 10x to the power of 4 becomes 10 over 5x to the power of 5. And then minus 2, the derivative of tangent is secant squared and a constant. So practically you're done. 2x to the power of 5 minus 2 tan x plus a constant. It's very straightforward, everybody. Okay, very straightforward. Okay. The first one was a little bit more interesting, okay, but it's really not too bad. How about this one? As always, whether we differentiate or integrate, if we happen to have one term in the denominator, we most of the time can simplify it, and that makes it easier to differentiate or integrate. So That means we are going to make up 3 fractions. I hope everybody is comfortable with that. So we're going to basically drop the t squared from the bottom. So what happens is this gives you 2. This gives you square root of t, or t to the power of 1/2. And this one, negative 1 over t squared, gives you negative t to the power of negative 2. Why are we writing it in this format? It makes it very easy to integrate. So 1 by 1, piece by piece, term by term. 2 gives you 2t. T to the power of 1/2, okay? You add 1 to 1/2 becomes 3/2, so 1/2 plus 1, and then divide by it, okay? Divide by 3/2. Then the same thing here, minus t to the power of negative 2 plus 1 over negative 2 plus 1, okay? So it's important to see this is 3/2, this is negative 1. And we don't need the constant because we are evaluating it from 1 to 9. And so the first one is 2t. The second one, division by 3/2 means multiplication by the reciprocal, 2/3. Okay. Then you have a negative sign up here, and another negative sign makes it positive sign, t to the power of negative 1 or 1 over t. Okay. I hope everybody is okay with that. It's really not that big of a deal. Okay. And so let's see what happens next. Well, now let's plug in everybody. Let's plug in 9 and let's plug in 1. Okay, let's plug in 9 and let's plug in 1. When we do that, this is what we get. Okay. 9 to the power of 3/2, that means square root of 9, cubed, which is 3 cubed, which is 27, divided by 3 is 9, 9 times 2 is 18, okay? The other one is 2 times 9, 18, plus 1 over 9, okay? And 1 to any power is 1. So I hope you realize that this is 18, this is 18, and this one is 1 over 9. Then minus 2, this one is 1, right? And so put them all together. So you have 18 and 18 and negative 2 and negative 1 and 1 over 9 and minus 2/3. The assumption is you can easily do the math on your own. 32 and 4/9 shouldn't be a problem, I hope. Okay, class? I hope it's fine with everybody. Sounds good? Any questions? Okay, class. So we are ready to move on. Again, I hope you realize many times the algebra behind this is a little bit longer, okay, than usual, or the basic math, I should call. But it's nevertheless, it's not too bad. All right. Again, we use identities to make life easier. You probably remember sine 2x is 2 sine x cosine x. So the sign drops. And the derivative of cosine is negative sign, but the integral is positive sign. So 2 sine x plus a constant. So I hope you realize using the identity makes it a piece of cake to finish the job. The next one, we know the answer is natural log. We just evaluate it from 2, okay? So ln 6 minus ln 3. If you left it as that, it's okay, but I hope you realize it's ln of 6/3 or 2. That is one of those logarithmic properties class. I hope you remember. all right, let's look at some applications. Um, the figure shows both displacements and distance traveled can be interpreted in the terms of areas under a velocity curve, okay? So distance is everything we cover, a sub 1, a sub 2, a sub 3. So the absolute value of v of t is integrated, but displacement is just a1 plus a3 minus a2. That one is negative. What do we mean by that? If we look at this concept class, if we go from point A, let's say this is point A, this is point B. We want to go from point A to point B, and we cover this distance. I hope you see that this is a distance. You got to calculate everything that you cover. So if you're driving class and you cover 700 miles to go from point A to point B, that is the distance that you have covered. However, if there was a straight line from A to B that was, let's say, 400 miles, that would be your displacement. So I hope you see the difference between the two. Distance versus displacement. You're just simply going from point A to point B. That is your displacement. And of course, acceleration, if you remember, the derivative of velocity is acceleration, and then the reverse process. So let's take a look at an example of this. We are given the velocity function v equals t squared minus 1 minus 6. Okay, everybody? And we want to find the displacement from 1 to 4. And displacement really means s of 4 minus s of 1, or just the integral of the velocity function from 1 to 4. Okay? That's what it means. And so let's do that. Plug in. Now, I hope you realize it becomes 1/3 t cubed minus 1/2 t squared minus 6t. Now you're going to plug in. Now, I'm not going to go over that. I'm going to assume everybody can do that. So you plug in number 4, gives you an answer, minus you plug in number 1, gives you an answer, and you're done. Negative 9/2 or negative 4.5 means, okay, the particle moved 4.5 meters towards the left. So let me just go back and tell you why. We always, if the units are given, we follow. So the velocity was meters per second, everybody, meters per second. So the distance and displacement are in meters. I hope everybody's clear on that. What about the distance? We have to take the same thing, but in an absolute value. Now, how do we get that one? I want to make sure we understand how this thing works and how we ended up with 1, 2, 3 with the negative and 3 to 4 with the positive. So I want to show you that using the sign graph, you have to figure out what's going on with v of t. So first and foremost, v of t has to be factored out, everybody. Okay, so v of t in factored format is what? T, let's just write the velocity function itself first. T squared minus t minus 6 is what? T plus 2 t minus 3. So I hope you realize that if you set this equal to 0, so this is t, this is the velocity. So at negative 2 is 0, at positive 3 is 0. And what we do, we are going from 1 to 4. So it's just on both sides of 3 that matters, nothing else, okay? So this is the only one that matters because we are going to go from 1 to 4. So to the left of 3, if you pick a number such as 0 and you plug in, okay, you get positive times negative, so this becomes negative. And to the right of 3, such as 4, you get positive. I hope you understand what I'm saying. I'm just plugging in the number into this and to figure out. This is called the sign graph. So that means it's negative to the left of 3, okay, and positive to the right of 3. So to the right of 3, we use the function itself. But because it's negative, to the left of 3, we use the negative of that to make it positive. In other words, because of this region being negative, we use minus here. This has got to do with using sign graph. I hope everybody understands what I'm saying here. And now you do the math. Again, this is a little bit tedious. It takes some time, but it's really not too bad. So minus t squared. So you get basically the same thing here, the same thing here for the second part from 3 to 4, and the opposite of that for the first part. So minus t cubed over 3 plus t squared over 2 plus 6t from 1 to 3, and the same thing from 3 to 4. Okay. And you plug in, I'm assuming everybody can do that, and you come up with the following number: 61 over 6 meters, precise, roughly 10.17. Your distance must always be positive, class. Your distance must always be positive because you are taking the integral of a positive function, absolute value of v of t, okay? It's remember, absolute value in the worst case is 0. And displacement could go either way. All right. Water flows from the bottom of a storage tank at a rate of R of t is 200 minus 40 liters per minute. We want to find the amount that is going to flow out for the first 10 minutes. This is the rate class, okay? This is the rate. So the amount really in essence is the antiderivative, is the integral, okay? So if this represents the rate, capital R of t is going to represent the amount of water, and it uses the accumulated change or net change theorem, where we are interested in finding the integral of a to b f of x dx. So in this case, we for the first 10 minutes, we are interested in finding the integral of lowercase r of t dt, which is a simple math. So 200 minus 4t, we are integrating 200t minus 2t squared. When you plug in 10, that gives you 200 times 10, 2000 minus 2 times 10 squared. This is 1800. This gives you 0 and 1800 liters. Let me just look at liters per minute. Let's look at this unit. So it is important to see how we arrive at units. The rate had units of liters per minute, therefore the amount has the units of liters. Okay, everybody? Now, of course, we could have found class capital R of t in general and then plug in the time. That's what I'm going to do. In the next example, I want to do both ways, okay? So we are given for a fish that starts life with a length of 1 centimeter and has a maximum length of 30 centimeters. This equation predicts the growth rate to be 29 e to the power minus x centimeters per year. And we want to pay attention to the units. Where x is the age of the fish, how long will it be after 4 years? I'm going to do 2 ways for you, but quickly, this is also the accumulated change. So if the length is capital L of x, then the growth rate L prime or dL dx, okay, is what's given. Okay, class. So capital L of x represents the length of a fish. So the growth rate is the derivative of that, and the amount of increase can be calculated using the integration, the amount of increase. Now, I hope you realize this is dividing by -1. Everybody, 29 divided by -1 minus 29 e to the power minus x from 0 to 4. You just got to plug in 4 and plug in 0. When you plug in 0, this becomes 1, by the way. Okay. And then you need a calculator, class. That's all. Okay. E to the power minus 4 minus 1 times -29. It becomes 28.4688. And remember that the length was 1 centimeter to begin with. So how long will it be after 4 years? Just add 1. And then I'm going to go with 1 decimal that they asked. Okay, class. So I suggest you use a lot of decimals and eventually do the rounding. If you don't do that, you end up with the wrong answer, class, what's called round off error. Okay, so make sure you do the rounding at the end. I want to go over the second method, class, quickly, and that is to find the equation that represents the length of a fish at any given time. In other words, everybody, I want to find L of x. Okay, and most of the job has been done. We want to integrate that. We get this one, but it's plus a constant, and the initial value was 1. So growth rate, okay, the amount of growth is the integral of that, and that gives you minus 29 e to the power minus x plus a constant, where L of 0 is 1, and now we can find the constant, and the constant becomes 30. Quickly, let me just show you why. Class, L of 0, so negative 29 e to the power minus 0 or 0 plus a constant is 1. I hope you see e to the power of 0 is 1, therefore c becomes 30. We get this formula. And now, what do we want? We want the answer after how long? 4 years, L of 4. And I hope you see it's the same answer. I haven't rounded this one. What is the advantage of this? If the question had a few parts, how long will the fish be after 4 years? Part A. How long will it be after, I don't know, 10 years? Part B, so on and so forth. All you have to do L of 4, L of 10, and you don't have to integrate again. So that would be the advantage of that. Either way is fine. Again, 1 gives you the amount of increase, and 1 gives you the general function you plug in. We want to find the area between the x-axis and the function y equals cosine x as we go from 0 to 3 pi over 2. I hope you realize that if we are evaluating the integral, it gives us the difference of areas. I can't emphasize this enough. Okay, class? But if we want the area, okay, so in other words, when we do this, if it's cosine, not absolute value, this is positive and this is negative because it's below the x-axis. And because of that, we need to use the absolute value, which means from 0 to pi over 2, we are in good shape. But from pi over 2 to 3 pi over 2, because it's negative, so we are going to use negative cosine x. So take a look at how we cut it into pieces. The portion which is positive, 0 to pi over 2, fine. But after that, it's below the x-axis is negative, then we can say minus cosine x. I hope everybody understands. That's exactly what we did when we looked at the velocity, okay, and the concept of a distance. And I looked at the sine graph. That's precisely the same concept. The graph is telling us what happens at pi over 2. Everybody remembers the graph of cosine. I hope, by the way, this thing continues, right? Remember, this continues, and this is one complete cycle. Okay. All right. Now it's easy. You just integrate cosine, and it gives you sine. Remember, the derivative of cosine is negative sine, but the integration is positive sine. So this gives you sine. This negative remains negative sine. Now plug in pi over 2 and 0, 3 pi over 2 and pi over 2. Okay. And so sine of pi over 2 is 1. This is 0. Okay. Minus sine of 3 pi over 2 is negative 1 minus positive 1, and see what happens. So this is 1 minus 0 minus, this is negative 1 minus positive 1. So this is negative 2, and with this negative becomes this negative 2. This is positive now, and 1, they add up to 3. So I hope everybody is okay with that. I suggest now definitely do this at home, class. In fact, you can use everything that we've done here and come up with an answer. Obviously, I'm saying the answer is not number 3. What we looked at was the area, the absolute value. Now you guys find the integral of cosine as we go from 0 to 3 pi over 2. They are slightly different, okay? And see what you get. All right. I hope everybody's okay with that. I'm going to look at one more example. I don't want to spend too much time on that. I'm interested again to just show you the process. So here's the next example and the last one. Again, the rate of increase is given, lowercase f, okay, as a very complicated function. And the reason why, because it's really a real world function. That's why the functions are not nice and easy to deal with. So f of x is 0.1762x squared minus 3.986x plus 22.68 centimeters per year. Let's just write that. Okay, I want everybody to pay attention to this. That means it's the rate. And so for x between 3 and 9 years, find the accumulated change in ram's horn from age of 3 to 9. That means basically you integrate from that. This is the accumulated change or the net change theorem, class. Capital F of x represents the actual length, okay? And so accumulated or the net change requires the integration of lowercase f from 3 to 9, which is this. Now, this is the reason I don't want to do that. The numbers are not nice. But again, I hope you realize the purpose of this question really are two things. Number one, real world examples. The questions may be a little bit involved. It's tedious to do the math, but it's really very straightforward, okay? So basically divide this, okay, what do I do? Let me divide this 0.1762 by 3x cubed minus divide this one minus 3.986 by 2x squared, and then 22.68x evaluated from 3 to 9. And believe me, I don't want to do that, but you get the picture. So plug in number 9 using a calculator, and then plug in number 3 using a calculator, and their difference is the answer. In centimeters, the units are extremely important to remember. Centimeters per year was the units of rate, so this becomes in centimeters.